Okay, so we're going to start simple harmonic motion and waves and sound, and we're going to combine a couple of chapters in the book. And I think I'll just have you do worksheets, so I don't think you'll need the book so much. But the first thing I'd like you to do is to, oh, this intro thing is doing, but the first thing I'd like you to do is to watch this video that I've embedded into PowerPoint. So you'll pause this video, take a second to watch this simple harmonic motion. If for some reason, I don't know if my recording of the video is going to work, but I'm going to put these notes with the lecture. So if for some reason it doesn't, just go to those notes and click on it. But there's some great animation there that I just can't do, and so please do that first. All right, so the first thing we're going to talk about after that is the farther the mass is pushed or pulled from its equilibrium position, the stronger the restoring force is going to be. So you saw this in the video, Hooke's Law. This force, this restoring force, is going to be negative because it's going to be opposite of what the displacement is. K is our spring constant, and you've calculated that in our bungee jumping lab. The lower the K value, the more springy it is, the higher the stiffer the spring. And so that's going to be based on the material it's made of and that kind of thing. And X is the distance displaced. And so we're going to take a look at what that means, but it's just the farther that you're pulling something from its equilibrium position, the greater that your X is going to be. So you saw this on the video, but if I have a spring like so, it's attached to an object, I can use some force to pull this out a bit, and then the restoring force pulling it back is what we're calculating here. This right here is our X distance, okay? And when I release this, it's going to come back from its maximum displacement, go through what's called the equilibrium position where it started at, and it's going to have enough momentum to come back like this. And as you saw from the video, if it was frictionless, it would just continue back and forth, and back and forth in simple harmonic motion. And so we need to look at that simple harmonic motion in more detail here. The second thing we're going to talk about, though, and we'll come back to that restoring force and the simple harmonic motion, but we can find this force a couple of different ways. We obviously have a way to calculate it. But if I graph force times the distance displaced, I will get a line, and the slope of that line is our K value. Now, I can go ahead and take force is equal to this K value times the X. But the only thing that I am calculating at that point is how much force is required at that point. So I certainly could take the restoring force here and say, okay, well, I've got a K value of 152 Newton meters. I'm just placing it by 0.25 meters. That was the maximum amount there. And I know that the restoring force toward the equilibrium position is going to be 38 newtons. Now that's just at that point, but you know how it is with the spring. When you compress it at first or stretch it at first, it doesn't take that much force, but the force is going to change at every instant as you compress it down to a certain point or pull it out to a certain point. And so that's going to be a changing amount. So when you go to find how much work is actually done, I know that you know the formula for work. It's force times distance, but be careful. You don't want to just take the force times the distance in this case, because that force is constantly changing. What we want to do is find the area under this graph, okay? And so what we would do is say, okay, well, we're going to integrate that area. And again, you don't need to know how to do this, but ultimately what you're going to need to do is pull that K out as a constant and integrate, and you come up with a formula of 1/2 kx squared. Okay, so if you want to know the work that's being done, that again is your energy formula for an elastic potential energy, or work energy, same thing. And so that is going to be your formula. So if you want to know the work that was done in compressing it by that much, this is what you'd want to do. So you'd say, okay, the work is going to be 1/2, whoops, times the K value times the distance that it is stretched squared. And that's where you're going to get the work that's being done. Okay, so we can calculate the restoring force. It's just going to be your K value times how much it's stretched by how much. At that point, that's how much is the restoring force. If you want to know the entire amount of work that it took to get to that point, you're going to want to use 1/2 kx squared. All right, so let's take the remainder of the video and just talk about some, not so much math as just some conceptual stuff here. So when I talk about the amplitude, that is the maximum distance displaced from the equilibrium point. And when we talk about a cycle, we're going to start at some point, and I've said, okay, let's start at positive A. And we're going to go to the equilibrium. We're then going to go to negative A, and then back to equilibrium, and then back to A. And that's going to be one cycle. So on the video, he was talking about this. When you have this spring, there's lots of different things you could use, but I would pull it out like so, and then this would be my positive A. It would come back to negative A, and then this is its equilibrium position. So in every situation, think about what that cycle would be. So, you don't have to start here. I was just saying, hey, you start here, come back here, that's a cycle. If you want to start at negative A and come back to negative A, or even start at equilibrium, come back to equilibrium, that's fine. So like here, a cycle would be from A to equilibrium to negative A, back to equilibrium, back to A, okay? Or wherever you want to start and come back to after one full cycle. Okay. The period is T. This is the time required for one complete cycle. And frequency, if you think about just standing at a point and watching this thing go by, how many cycles go by per second? And so frequency is 1 over the period, or 1 over T. So those are some things you might want to jot down. And many natural processes follow simple harmonic motion, and we're going to look at a few of them. A pendulum, a mass on a string. I don't have to do it this way. I could just do a string or a spring that's up and down like this. And uniform circular motion. So I do have another video I want you to watch, and this one is really important. Oops, I just skipped right over it, but please pause it. Watch that video. It's really important to get a picture in your head. I cannot do it justice here, so doing some animation is definitely worth it. Well, let's take a look. I did the spring back and forth, but let's look at a pendulum. And here I have a pendulum that is at equilibrium, and I can pull it out of equilibrium. Okay, my circles are pretty bad there, but can pull it out of equilibrium. And so what's going to happen here is I could think of this as negative A and positive A amplitude. And as we look at this, this is my equilibrium position, and then one cycle, and this is going to be important for doing some problems. One cycle, I could start here and say, okay, here, 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 and here. That is one cycle. So really important that you know what a cycle is there. Now, as you might have seen, I can also graph this, and we look at a sine curve basically, because like this, I say, okay, I'm going to start here, amplitude A. I'm going to go to from positive A. I'm going to go to negative A, back again to equilibrium, and then back again to positive A. So if I were to graph this motion, or if I were able to get a pendulum that would like let out a little bit of sand or ink or something like that, and I'd swing it back and forth and move the paper, I would get this sine curve here. So this would be amplitude and amplitude, and what I've drawn here is one cycle. Now you might remember that I did a explanation where we talked about Newton's law of gravitation, and I said, if you were able to draw, or I could draw it, I can't do it, but if you were able to drill a hole through the center of the Earth, and you were to be able to stand there, and then you could go plummeting to the center of the Earth. And remember, with Newton's law of gravitation, the distance from the center of the object is where you calculate your r. So when you have g is equal to mass 1 times mass 2 over the distance squared between them, if you have no distance, you have no gravitational pull. So if I were to stand here, my velocity would be 0, but my acceleration would be a maximum of 9.8 meters per second squared. Now, as I go, if I jump off the edge, I go plummeting to the center of the Earth. At the very center of the Earth is what we call our equilibrium position. Okay, and this is important to understand as we look at simple harmonic motion and circular motion too. So up here, this would be my maximum A, okay, so to speak. And this would be my negative A. Okay, so once I got to the center here, my velocity would be at a maximum. I'd be just going really, really fast. But my acceleration would be 0. But I'd have so much speed at this point, I'd go flying over here at my maximum speed until I got to the very edge of the other side of the Earth, where my velocity again would be 0. And my acceleration would be a maximum of negative 9.8 meters per second squared. So there's something analogous here to terminal velocity as well, so you kind of think about that. But as you go back and forth here, this would be simple harmonic motion. Up and down like that. And one cycle would be from here back to here. That would be one cycle. And that would take 90 minutes, and so does a satellite. All right, so from your video from before, kind of keep that in mind what's going on here. I'm just going to show you a couple of pictures, and I want you to just think about this. If I'm talking about something moving on like a turntable, one of those old-fashioned album players, I'm just going to, just a couple of things for thought here. First of all, notice when he was doing this, he had something on that turntable that was a constant angular speed. Now be careful, because it will not be a constant speed when we look at it from simple harmonic motion. So, constant angular speed. So let's look at a couple of different pictures here. Let's say that I have a v sub t here, a v sub t, a tangential velocity, remember that, and a v sub t here. So we'll look at kind of some extreme measures. And then for centripetal acceleration, of course you remember that. That is centripetal acceleration for constant angular motion is going to be toward the center. There's still a directional change, right? A sub c and a sub c. All right. So what I'm talking about is not so much this as I'm talking about how does this project onto this this tracker. Okay, so a couple of things I want you to notice, and we could put some trig to this, but I'd rather you just understood the concepts rather than us trying to do some trig and plug and chug and not really understanding that. Let's say that we talk about this one as negative A, talk about this one as positive A, and we talk about this as equilibrium. So as this object is moving around in constant angular speed, we see that the tangential velocity in the simple harmonic motion is changing and the acceleration is changing. So a couple of things to note here from these vectors, that notice here that v sub t gets larger from negative A to equilibrium, where v sub t is at a maximum here. We could talk about this as being the entire part of v sub t that we're looking at. And notice that at equilibrium, what's happening here is v sub t is at a maximum. Okay, so this is velocity will be at a maximum. X, the displacement, is at 0, right? So because from equilibrium, you get x is further and further away till you get maximum amplitude.